Welcome back, chat. Cool. So this is linear impulse as we're looking at it. And then what if I want to do just something a little bit crazy and I want to talk, instead of about linear motion, we make the change to angular. Instead of force, what causes angular motion? It's still kind of force, but a little different. Torque. So here we go. We have some lovely torque here. And we take torque times time. And we're going to get a change in momentum again, all the same. But we have to make some changes. Linearly, it's mass times velocity. What about angularly? When we start thinking about something spinning, that mass idea gets a little bit more complex. Instead of mass, what do we use? The moment. Love it. And how should I write it? Capital I. Cool. So here it is. And then instead of angular velocity, we just simply, instead of linear velocity, we just use a change in angular velocity. Sorry? So we can, if we were to take that omega f minus omega I, that's change in angular velocity. If we were to divide both sides by time, that's our angular acceleration. So that's where that alpha would show back up. Okay, from these two ideas, we have impulse momentum theorem. We have linear on top, we have angular on the bottom. Let's do a problem. Like, today's pretty chill, and we should be able to knock out a couple things. All right, now, I want to make a couple little comments, and this is kind of to get us in, and then we're going to work an example. Is this the last thing you have, angular impulse? Okay, so I want a few simple notes here. We're just going to connect some pieces. It is entirely up to you how much you want to write, but conceptually, we're going to make some stuff click. Okay, in the linear situation, if my force, right here, I'm going to write it as the net force acting. If my net force is 0, is it any change at all in velocity if I don't add force? Can you make something change its speed, its velocity, direction, anything like that if you don't apply force? No, because Newton says if you don't act on it, nothing happens. Which means if we say, hey, the net force is 0 newtons, do you guys agree that this implies that my momentum, rho, is constant? It does not change. Okay, if this doesn't change, and if we're acting with an object, it's not like its mass can suddenly change either. So we see that, all right, no change in force or no additional force being put into this. Rho can't change, velocity can't change. Nothing crazy, right? Okay, let's switch here. This is our linear situation. Let's look about the other situation. If I were a wonderful ballerina or a figure skater, and I'm spinning, like if we've ever watched somebody spin, can I change my speed without applying force? Like imagine somebody spinning. You say no, but have you guys seen figure skating before? Okay, if somebody's spinning, I'm trying to think, I don't want to just watch because it's going to be a random video to find. Do people change how fast they spin? Ooh, what are you doing? Here I am spinning super fast. What if I want to slow down? Oh, I get crazy, right? The legs come out and we slow down. Why am I slowing down? I'm not applying force. That's a good thought, but not quite. What changes instead of mass, because we don't change your mass, but your moment changes, doesn't it? If I change my shape, I change how fast I spin. You guys have all seen it when you play on those spinny things, I imagine, like the one at Pirate Park. If you stick your arm out, you go slower. If you stick your arm in, you go faster. Okay, you are changing your moment in that situation. So for angular stuff, it is worth mentioning and thinking about that, hey, we can't change our mass. However, if we change shape, which is like we're still human, right? But arms up or arms out, then we get a change in the moment. Change in moment. Okay, now if we get a change in moment, something else must also change. The moment of inertia just says how our mass, how much force or torque it takes to turn us. If we change a moment, I'm actually not changing the force, not changing the torque, but I am changing my speed. We see that it has to go slower or faster depending on your shape. So I'm going to say this implies change in omega, which last little piece, this changes the angular momentum, L. And I know that I hate it, and I'm going to use a fancy L. I forgot that I was doing that. Okay. Now, as we look at this, it turns out that there's some awesome things that happen. There's a thing in physics called the three-body problem. Have we talked about three-body problem? Maybe a little bit, whether it was in here or not. If you have two stars orbiting, they do a bunch of crazy stuff, and it does happen. Like, they'll start speeding up, they'll go crazy. If you have three things orbiting, we can't predict it. Like, our math just isn't good enough yet. It's called chaos. So as we look at this, it turns out that if you were to look at any star system where the stars are interacting like this out in the universe, you're going to see changes in all of this. All the angular momentums, all of the velocities. Stars can whip each other apart. Like, it's crazy how fast they get going. Okay, now, other places your book likes to use figure skaters is a really easy one. Divers, like professional divers doing crazy stunts, is also the same thing. If you want to do front flips, how do you tuck your knees? Dang it. If you want to do front flips, what do you do with your knees? You tuck them. And if you don't want to belly flop, weird. You have to unwind yourself at the correct time to slow yourself down so you land hands first, right? Okay, these things, their applications are everywhere. I'm not going to draw a person, but let's knock out an example. So, for this, I'm going to not write it all down. You guys, I want you to have it labeled as follows. Example 2 is the one that we're going to look at, and I'll put it up on the board for you. But we're going to find this on page 242. And I will pause this. Today, just so you guys are aware, we're going to do 1, maybe 2 examples. I'm going to give you some time to work on this stuff so that we don't get too wildly far ahead of your peers who are coming back today. Cool. All right, so I'm going to keep this up on the board for a second. I want you guys to read through this problem. If you have your book open, awesome. If you don't, equally awesome. We are going to try to make sense of this problem. We have example problem 2. I'll let you guys read it. If you're watching this on a video, go ahead and pause it, and we'll come back together to look at this in just a moment. So we'll see you cool cats in 3, 2, 1. So let's dig in. Looking at this, what would you like me to write down? Can I get one known from you, number Sean? Okay, so the time it takes to stop in the end is going to be 3 seconds. I agree. Love it. Riley, give me another one. Say it again. So you're close. I'm going to say initial, and then I'm going to write one more extra thing, because I agree with you. It's 2.5 revolutions or rotations per second, right? Okay, now here's the issue that I have with this. When we're dealing with angular velocity, we don't talk in rotations per second. We have a way to measure the amount of rotation that's been made that's not arbitrary. We can switch this to radians. If I spin one full circle, how many radians do I turn? Almost. 2 pi. So 2.5 circles is 2 pi, 4 pi, 5 pi. Everybody agree and cool with that? 2.5 circles is just 5 pi radians. So I'm going to switch this out. 5 pi, and this is irritating, but I'm going to say per second. Cool, because there's no real unit on it. Okay. Delilah, can you give me omega final? 0. Love it. And it could be rotations per second, but since we're already here, it's just 0 radians per second. I'm good with that. Totally anything else? I need the moment. And checking it out, we have I equals 0, and I'm going to make that nicer. 0.5 kilogram times meters squared. Okay, so this is 1/2, which means this person isn't a ring, which is a good sign for somebody that's a human. They're usually not. Cool. We have all this information, and it doesn't really feel like it, but we're trying to find at least 2 different things, and they just kind of hide it in this problem. Instead of doing A and B, let's see. What's one thing we're asked to find here, Nick?
Average torque.
So I'm going to say let's find torque. Cool. What else? Are we asked to find impulse? What is the value in sine? So how do we find that? Like, how would you write it down?
F delta D.
You're so close. We're not linear.
Oh.
Instead of F, we're going to use some other weird torque. Good. So tau is this letter. So we need to find this. Anything else we need? how would you write that one? It is the L. We will not take the L, but we got it. Cool. All right. We have all of this information that we need to find out of this deal. And it's all here. Do we want to do this one together? Do you guys want to try to talk it out and get a head start on me? What are you feeling this morning? Together? I'm good with that. All right. So I don't really care where we start. Let's see. If I'm looking for all these things, I would probably begin this problem the same way that we did all the other angular impulse or impulse momentum theorems. Is there a version of the impulse momentum theorem for angular stuff? Indeed, there is. And I'm going to just write equations and work and all that good stuff. What is it? What is angular impulse momentum theorem?
Torque delta T equals inertia and delta W.
So I'm going to call it omega, and I'm going to write it like this, but I agree with you, Nick. Cool. Awesome. Nice job. Okay, looking at this, I think that we have pretty much everything that we need. What would you guys like to find first? Do we have the moment and my velocities? Do we have the time? Hey, let's find this one first since it's already solved for tau delta t. And then once we get that answer, we just simply divide by delta t. We'll get tau out of the deal. And then we'll see where we're at. Cool. So let's check it out. This is exactly equal to, and I'll just keep it here. I'm not going to change it at all. What's my moment? That it is. And initial velocity was, or sorry, final velocity? I think it's 0 minus, how about initial? Try again. I like it. You're not wrong, but there's a better way to write it. We did something extra. 2.5 is fine, but I want to call it this. And only because when we play the unit game here in a second, you'll see why. Now, I'm going to make that pi nicer. Anybody ever play the unit game when you're doing problems? But we all like to play it together, so I'm cool with that. I'm going to do a little thinking. This is entirely up to you if you want to write it. I would always recommend it. Here's kilogram meters squared. And this is in radians per second. Cool. I'm feeling all right at this point in time. We'll see where else we wind up momentarily, but let's just think this out. Can we do this problem in our heads? Half of 5 pi, or negative 5 pi in that situation. 2.5 pi. 2.5 pi. And grab your calculators. Let's get an approximation for this, and we'll see what we come up with. And it's negative, rather. So negative, I'm thinking it's 7 point something. 8.5 kilogram meters squared per second. Okay, we have our angular impulse. Cool. Now, moving forward, if we have this, it is easy enough to find, I think, our tau value. We just simply divide each side by what? From this, one step away from getting just tau alone. Yeah, let's divide by time. So we take this lovely thing, negative 7.85, and I'll do the unit game here again in just a second, divided by, how much time does this take? Okay, so there's that number. And, well, gosh, I think this is about negative 2 point something. 6.1. And that is, let's see here. Let's play around with the units for just a second. This was kilogram meters squared per second divided by seconds. So I'm just going to multiply by 1 over seconds. And let's just see what shakes out. This is kilogram meters per second squared times meters, I think. Now, I rearranged it a little bit, right? because it would actually be kilogram meter squared per second squared, but I did this for a reason. This looks like mass times distance over time. Whoa, distance. What am I talking about? Mass times velocity, sorry. This is a Newton. Kilogram meter per second squared. Mass times acceleration, meters per second squared, and kilogram. Okay, so this is Newton. Is torque measured in Newton meters? Or foot-pounds if we're in English? Cool. So we got that one. I'm good with it. One last little piece. We are also looking for L. What does L represent again? Angular momentum. So as we're looking at this, and I want to see, does it say angular momentum or does it say average angular momentum? What is this value and sign of the angular impulse? Average torque. And what is his angular momentum? So it's just the angular momentum to begin with, right? So, gosh, how do we find that? We need one more little equation, and maybe we could have done that one first. You just take, instead of, sorry, one more time. With regular stuff, what's momentum? It's just mass times, almost. That's force.
Magnitude.
Good word, not what I'm looking for here. How do we find momentum? And if you want to look at linear, I'm fine with that, because it's the same idea, we just switch it to angles. Mass times something. Rho equals what? We're going to find it here. So here's where we started. Mass times velocity. And then we changed it to moment times angular acceleration, and then we divided by time to get that afterward. I think it's just mass times velocity, but let's switch that to linear. Instead of mass, what do we use if it's angular? I think you can find it. Totally, what do you want to use instead of mass? So, not quite impulse. The moment of inertia, that's the I hint. And instead of angular velocity v, we just write it here. Okay, we are looking at the angular momentum to begin with. Well, let's check. 0.5 times, what was my initial? 5 pi. Love it. And check it out. We already know this number. Now, notice, there's no change, right? It's not final minus initial or anything like that, so we don't have to worry about the sign. We're going to see a relationship here. I think it's 7.85 again, isn't it? Kilogram meters squared per second. Okay. Now, as we look at these problems, there is no difference other than the letters or the symbols that we use to represent them. It is essentially the same thing. If we wind up going any speed but 0, we are going to see a different change in angular momentum than we wound up with here. If we end at 0, it's always going to be the same. Cool. All right. These problems feel okay, feel awful. Okay, I'm going to give you some time to get a little bit of practice on them. If we need to do another one, I'll hold the video. Before moving on, any last lingering questions before I let you guys try to knock out a couple of these? All right. So, today's homework, or work time for a bit, and let's see here. Yep, I'm good with it. Homework that we will start in class, we'll call this homework 9.1. And you will find this on page 243. Now, rather than just giving you a ton of example problems, which we can do another one if you'd like, I want you guys to knock out the conceptual side with 1 or 2 in there. So I want you to do problems 10 through 15. Cool. I'm going to pause this here so that if we have to work a problem together, I will not do the exact problem that you have to do, but if we need to do another one together, I'm good with it. We got lots of time to work on this. Not a threat, but if we finish, we'll get a head start on something else. Cool. All right. I'll give us a little bit of time.